Hello friends, welcome back to my YouTube channel. In this class I am going to discuss three more problems of chapter 6 of P.K.Nag's Engineering Thermodynamics. In my previous lecture I have already solved 16 problems, so I am going to start from 6.17. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. The question number 6.17 is like this. Consider an engine in outer space which operates on the Carnot cycle. That means the engine is a reversible engine because it operates on the Carnot cycle. The only way in which heat can be transferred from the engine is by radiation. You know that heat engine some heat is rejected, not the complete heat input is converted into work output. Some heat is rejected to sink, and in the question it is given that whatever heat is rejected to the sink can be transferred from the engine, and that transfer of heat takes place through the mode of radiation. The rate at which heat is radiated is proportional to the fourth power of the absolute temperature and to the area of the radiating surface. So that for a given power output and a given T1, of course, the power output is given and source temperature T1 is given, then the area of the radiator will be minimum when T2 upon T1 is equal to 3 by 4. So, suppose the reversible heat engine operates between two temperatures. One is source temperature and other one is sink temperature. This is sink and this is source, and this is a reversible heat engine. Suppose the heat supplied to this heat engine is Q1, heat rejected is Q2. If you take the rate of heat input and rate of work output, then you can place dot on it. This is the power output of this reversible heat engine. Suppose this is the rate of heat input and this is the rate of heat rejection. Since it is the question, it is given that for given power output, that means this is W dot. You see, this heat is rejected by the heat engine, and out of this heat input Q1 dot, rate of heat input Q1 dot, W dot is the power produced by this reversible heat engine, and Q2 dot is the heat rejected to low temperature sink. And heat can be transferred from this sink, from this radiating surface, through the mode of radiation. You know, there are three modes of heat transfer: conduction, convection and radiation. And it is given that in the question that the heat can be transferred from this radiating surface, and that heat, whatever heat, rate of heat that is rejected to this low temperature sink can be radiated, and that is Q2 dot is equal to K A T to the power 4. Since it is given in the question that rate of heat radiated is proportional to the fourth power of absolute temperature. Fourth power of absolute temperature, that means T2 raised to the power 4. And again, the area of the radiating surface. Area of the radiating surface. It is given in the question. Area of the radiating surface and fourth power of the absolute temperature. T2 to the power 4, as well as the area of the radiating surface, and K is a proportionality constant. So I can write like this: rate of heat radiated from this low temperature sink is nothing but Ka T2 to the power 4. So we can calculate the efficiency of this reversible heat engine. You know, efficiency is nothing but W dot divided by Q1 dot, and this is equal to, efficiency of any reversible heat engine is 1 minus sink temperature expressed in Kelvin divided by source temperature expressed in Kelvin. This is equal to, and for a reversible heat engine according to thermodynamic temperature scale, Q1 dot divided by T1 is equal to Q2 dot divided by T2, and that relationship holds good only for a reversible heat engine, not for any other heat engine. So that means Q1 dot divided by T1 equal to Q2 dot divided by T2, and I can write this further: Q1 dot minus Q2 dot divided by T1 minus T2, and this is nothing but your rate of power output. This is the heat supplied to the heat engine and this is the heat rejected. So net heat input will be Q1 dot minus Q2 dot. That is just W dot. Sigma W cycle is equal to sigma Q cycle according to first law of thermodynamics. So Q1 dot minus Q2 dot, Q1 dot minus Q2 dot, I can write for Q1 dot minus Q2 dot W dot, where W dot is the net power output of the reversible heat engine. So from this relationship I can write Q2 dot divided by T2 is equal to W dot divided by T1 minus T2. So W dot divided by T1 minus T2 is equal to, in place of Q2 dot I can write Ka T2 raised to the power 4, where K is the proportionality constant, A is the area of this radiating panel, T2 is the absolute temperature of this radiating surface. So I can write from this, in place of Q2 dot I can write Ka T2 raised to the power 4 divided by T1 minus, this is Q2 dot divided by T2. So T2, this is Ka, Q2 dot divided by T2 is equal to W dot by T1 minus T2. So W dot by T1 minus T2 is equal to, in place of Q2 dot I will write Ka T to the power 4 and T2 is there, so I will write T2 in the denominator, and this comes out to be Ka T2Q. From this I can get A equal to W dot divided by K T2Q multiplied by T1 minus T2. This is equal to, A is equal to W dot divided by K T2 raised to the power 3 multiplied by T1 minus T2. So this is equal to W dot divided by K T1 multiplied by T2 raised to the power 3 minus T2 raised to the power 4. This is the expression for area, and in the question it is given that this area for a given power output and given T1, area of the radiator will be minimum. So this is the expression for area is equal to W dot. This is just expression for area. Area is equal to W dot divided by K into T1 T2 to the power 3 minus T2 raised to the power 4 for a given power output. For a given power output power output, that is W dot is constant and the value of T1. T1 is also constant. So area being a function of these three things, W dot, T1 and T2, Ki being a constant. So if at all with anything area will vary, that will be with respect to T2 only, temperature of radiating surface. Since W dot and T1 can't be changed, they are constant. According to question, for a given power output, that is W dot is which is constant and T1 is also constant. So if at all we can change area, that can be done with respect to T2 only. So for finding out the value of T2 at which area will be minimum, we have to differentiate area with respect to T2 only and get equate it to 0. According to the principle of calculus, when a function is either maximum or minimum, first derivative must be 0. So on differentiating area with respect to T2, I will get in place of area I will write W dot divided by K, T1 T2 to the power 3 minus T2 to the power 4 equal to 0. Now I will differentiate. So W dot by K, and this is I will write T1 T2 to the power 3 minus T2 to the power 4 minus 1 equal to 0. On differentiating, I will get W dot by K is a constant which can be taken outside. Or first I will differentiate this. So according to the chain differentiation, this will be T1 T2 to the power 3 minus T2 to the power 4, and this is minus 1 minus 1 minus 1, that is minus 2. Simply I will write minus sign prior to this, and if I further differentiate this term with respect to T2 according to the principle of chain differentiation, this will be equal to 0, or minus W dot by K T1 T2 to the power 3 minus T2 to the power 4 minus 2 raised to the power minus 2, 3T1 T2 square minus 4T2 to the power 3 equal to 0. Out of these three terms, product of three terms, you see how can this whole expression be 0? This cannot be 0 because it is given that this is some power output is there and this term cannot be 0. So out of these two terms, I have to find out at which point the function will assume 0 value. You see this term, when it will be 0, this term will be 0 only when is equal to 0, which is not possible, because when will this term be 0? When will this term be 0? Only when T1 T2 to the power 3 minus T2 to the power 4 equal to 0, or T1 T2 T1 multiplied by T2 raised to the power 3 is equal to T2 to the power 4, or T1 equal to this is equal to T2, which is not at all possible. T1 can never be equal to T2. This term is 0 only when T1 is equal to T2, which is not possible anyway. T1 cannot be equal to T2. If T1 is equal to T2, no heat engine can operate between those two temperatures. There must be some temperature difference for any motive power to be produced. There must be some temperature difference between source and sink. So this term cannot be 0. So only this term can be 0 to make this whole expression 0. So third term is, you see, third term is 3T1 T2 square minus 4 multiplied by T2 raised to the power 3 is equal to 0, or 3T1 T2 square is equal to 4T2 raised to the power 3, or 3T1 is equal to 4T2 raised to the power 3. By transposing T2 square to this side is equal to T2, or I can say T2 is equal to 3T1 divided by 4. T2 is equal to 3T1 by 4, or I can say T2 upon T1 is equal to 3 by 4. T2 by T1 is equal to 3 by 4. You see, this is the point at which the first derivative of area with respect to T2 is 0. But we are not sure that at this point the function area will be minimum. For that, we have to find out the second order derivative, that is dou square A upon dou T2 square. And on finding out where at T2 is equal to 3T1 by 4, and you will definitely find that this will be greater than 0 at this point. If you find out the second order derivative dou square A by dou T2 square at this point T2 is equal to 3T1 upon 4, you will definitely find that this is positive. So that means when second order, first order derivative at a point is 0 and second order derivative is positive, means function is minimum at that point. Had this been negative, the point would have been a maximum point. So you will definitely find out at this point, if you calculate the second order derivative, you will definitely find out a positive quantity, and especially at this value T2 is equal to 3T1 by 4. So then only you will be sure that this is a point of minimum. So we have only one point at which the first order derivative is 0. So this is what has been asked in the question. To prove that, this is, you see, T2 by T1 is equal to 3 by 4, and we just proved it. T2 by T1 is equal to 3 by 4, at which the area of the radiator will be minimum. Area A will be minimum for a given output and T1. W and T1 are constant, and we can change area with respect to T2 only, and at this point when T2 by T1 is 3 by 4, area will be minimum. So next question. 6.818, it takes 10 kilowatt to keep the interior of a certain house at 20 degrees Celsius when the outside temperature is 0 degrees Celsius. This heat flow is usually obtained directly by burning gas or oil. Calculate the power required if the 10 kilowatt heat flow were supplied by operating a reversible engine with the house as the upper reservoir and the outside surroundings as the lower reservoir, so that the power were used only to perform work needed to operate the engine. You see, the house is at 20 degrees Celsius, and when in winter, when the outside temperature is 0 degrees Celsius, or in terms of Kelvin, this is 273 Kelvin, and in terms of Kelvin this is 293 Kelvin, and you need a heat pump to maintain the temperature of the house in winter at this level when the outside temperature is quite less, that is at 0 degrees Celsius. So you need, according to question, you need 10 kilowatt to maintain the temperature of the room at 20 degrees Celsius, and this 10 kilowatt is obtained by burning the gas oil. Suppose we can also use the resistance heater for heating the room by using directly electricity for heating the room, and at that time you have to put in 10 kilowatt of electrical energy, and that will be converted into 10 kilowatt of heat energy. But in this case, if you use heat pump, you will be at a thermodynamically advantageous position, because to find out this 10 kilowatt heat which is needed to maintain the temperature of the room at 20 degrees Celsius when the outside temperature is 0 degrees Celsius, we have to give less power. We have to give much less power. How? You see, if we drive this heat pump with the help of a heat engine, that means whatever work is produced by a heat engine, if we use that power, we know that for driving a heat pump or refrigerator we need some power input, and that power input if is supplied by a reversible heat engine, and this W will be quite less than 10 kilowatt. If this W will be quite less than 10 kilowatt, because COP of heat pump is always, COP of heat pump is this heat divided by W. So this is work input, this comes from a reversible heat engine. So if this ratio, this heat divided by this heat is to be provided to the house consistently to maintain the temperature of the house at this level, and if this heat input is greater than, actually if this heat that is transferred to the house is greater than the work input, obviously the work input will be less than this 10 kilowatt. But if you use resistance heater, you have to supply that 10 kilowatt of electrical energy, that is a high grade energy, and you are converting it into a equal amount of low grade energy, that is 10 kilowatt of heat. But in this case you have to provide a less amount of work, very less amount of work. You see, COP of this heat pump, COP of this heat pump is, this temperature divided by difference between these two temperatures. If the heat pump is acting in a reversible manner, that means 293 divided by 293 minus 273, that is equal to 293 divided by 20. This is the COP of maximum COP or COP of a reversible heat pump, and that is again equal to 10 kilowatt divided by work input. 10 kilowatt COP of heat pump is Q divided by W. So 10 kilowatt divided by W is equal to 293 divided by 20. 293 divided by 20. W is equal to 10 multiplied by 20 divided by 293, this much of kilowatt. This is equal to 0.683 kilowatt or 683 watt. So you see, on supplying a mere amount of 0.683 kilowatt work input, we can produce this amount of 10 kilowatt, or we can transfer this 10 kilowatt amount of heat to the desired to the room to maintain the temperature, to maintain the room temperature at 20 degrees Celsius. That means we are supplying only 0.68 kilowatt and we are able to transfer 10 kilowatt of heat. On the other hand, if we use direct heating, resistance heating, then you have to supply 10 kilowatt of electrical energy, and you can only obtain 10 kilowatt of heat energy. So this is quite wasteful. Resistance heating or direct heating is always wasteful, and if you use heat pump to heat a room, that will be a very advantageous thing. So this was 6.18. Next is 6.19. Prove that the COP of a reversible refrigerator operating between two given temperatures is the maximum. COP of a reversible refrigerator operating between two given temperatures is the maximum. So we have to prove this. You see, suppose there are two temperature limits. This is high temperature limits and this is low temperature limits. And there are two refrigerators operating. One is not reversible and other one is reversible. Suppose this is and this refrigerator B is a reversible one. This refrigerator B is a reversible one, whereas A, this is suppose A is not a reversible refrigerator, and this one is a reversible refrigerator. Let Q1A is the heat input to Q1A. Let Q1A is equal to Q1B is equal to Q1. If you supply equal amount of heat, if you transfer equal amount of heat from low temperature reservoir, this T2 is less than obviously T1. You know, refrigerator are devices which transfers heat from low temperature to high temperature reservoir. So this one is a reversible refrigerator, reversible, and this one is not reversible. Suppose B is reversible and A is not reversible. And if you supply equal amount of heat, if you both these refrigerators transfer equal amount of heat from low temperature T2 to high temperature T1, we have to prove that the COP of B is greater than COP of A. You see, this is suppose Q2A. Q2A is nothing but Q1A plus WA, and this is suppose Q2B. That is nothing but this work input is suppose WB. Q1B plus WB. You know, refrigerator requires some work input. Here WA is the work input for refrigerator A, which is not reversible, and WB is the work input for refrigerator B, which is reversible. And we have to prove that the COP of reversible refrigerator is higher than the COP of any other refrigerator or irreversible refrigerator, and that means COP of reversible refrigerator is the maximum COP between two operating temperatures. You see, so we will assume that, let's assume that the reverse is true. Whatever statement is given in the question, that is the COP of reversible refrigerator is higher, we will assume that COP of other refrigerator is higher than the COP of reversible refrigerator. COP of A, which is not a reversible refrigerator, let's assume that it is greater than COP of B. That means you see COP of refrigerator is desired effect divided by work input. So the COP of refrigerator A is Q1A divided by WA. That means Q1A divided by WA is greater than Q1B divided by WB. Desired effect by work input, or Q1A, we have already assumed that Q1A is equal to Q1B is equal to suppose Q1. So I can write Q1 divided by WA is greater than Q1 divided by WB. So from this we can conclude that WB is greater than WA. When this inequality holds good, we can write that WB is greater than WA or WA is less than WB. You know, the refrigerator B is a reversible refrigerator. Refrigerator B is a reversible refrigerator. So I can reverse this refrigerator B. I can reverse this refrigerator B. Reversible, when we just reverse any cyclic device, what happens? The magnitude of this all these energy interactions in terms of heat and work remains same, but the directions are reversed. So this Q1B will be there, but that direction will be like this, not like this. Direction will be changed. And this WB is here work input. In case of reversed refrigerator, it will be work output, WB. And Q2B will be there, but that will be like this. That will be like this. So on reversing refrigerator B, because this is the only reversible refrigerator, A is not reversible, so we can reverse the refrigerator B only. On reversing refrigerator B, I will get, this is suppose T1, this is suppose T2, and refrigerator is so on reversing the directions will get changed, and this will be Q2B, and this will be Q1B, and this will be WB. You see, this is becoming a work producing device. On reversing, this becomes a work producing device. So reversed refrigerator B, it becomes a work producing machine. You see, on combining this, you see, we know that we have already assumed that Q1A is equal to Q1B. So in this case, whatever heat is rejected by this, actually this becomes a heat engine. Whatever heat is rejected, that goes to this refrigerator. So this reservoir T2 is eliminated, because since we have already assumed in the beginning that Q1A is equal to Q1B is equal to Q1. So whatever heat is discharged by this device to this low temperature reservoir goes on directly to this refrigerator, and there is no need of this temperature reservoir T2. This heat, whatever is rejected by this device, goes directly to this device. So need of this low temperature reservoir is eliminated, which is violative of Kelvin-Planck statement of second law of thermodynamics. Because we know that according to Kelvin-Planck statement, for a heat engine to produce network output, it has to exchange heat with two reservoirs. It can never produce network output by exchanging heat with only one reservoir. If you find out the equivalent of this combined system, if you find out the equivalent of this combined system, that is refrigerator and a reversed refrigerator, you will find out a heat engine. You will find out a heat engine. The combined system will be a heat engine. This is a combined heat system, equivalent system of this combined system, and this will be a heat engine which will receive Q2B minus Q2A from T1. You see, in this case, if you consider the higher temperature reservoir, net heat that is coming out of this higher temperature reservoir is Q2B minus Q2A, because this heat is going to this refrigerator and this heat is coming out of this. So net, you will find that Q2A is less than Q2B, because Q1A is equal to Q1B. But since in the first case what we found is WA is less than WB, so that means Q1A plus WA is less than Q1B plus here Q1A plus WA is less than Q1B plus WB, because we have ultimately found that WA is less than WB and Q1A is equal to Q1B. Matlab Q2A is less than Q2B. So more Q2A is less than Q2B. So here Q2B is coming out of this reservoir and Q2A is going into the reservoir. That means net heat is flowing out of this high temperature reservoir and this heat is coming out of this high temperature reservoir. What happens in and that happens in heat engine. So heat always comes from a high temperature reservoir, and the net work output here, since WA is less than WB, and here in the combined system WB is the net work output and WA is the input. So if you consider the combined system, the net work will be produced, not consumed, because WB is greater than WA. So net work produced will be WB minus WA, and no heat will be rejected to, there will be no low temperature reservoir, there will be no heat rejection. And if you calculate, you will find that Q2B minus Q2A is also equal to WB minus WA. From this diagram you will be find out Q2B minus Q2A is equal to WB minus WA, and there is no low temperature reservoir. See, here also it is proved that whatever heat is rejected by this device goes on directly to the refrigerator, and then some work is consumed, and then heat is rejected to the high temperature reservoir. So that means here the equivalent of this combined system is a heat engine which extracts this much amount of heat from high temperature reservoir and rejects no heat and completely convert this net heat input into net work output. This net heat input into net work output. You see, if you want to prove that this amount is always equal to this amount so that heat rejected is 0, you can prove that. You see, Q2B minus Q2A minus, if you subtract this amount from this, you will find that this is 0, minus WB minus WA. This is equal to Q2B minus Q2A minus WB plus WA. This is equal to Q2B minus WB minus Q2A minus WA, and this is equal to Q2B minus WB. This is Q2B minus WB is nothing but Q1B according to first law of thermodynamics. When a device completes a cyclic process, net एनर्जी इनपुट इज इक्वल टू नेट एनर्जी आउटपुट. सो यहाँ से एनर्जी क्या क्या एनर्जी आता है सिस्टम को, Q1B प्लस WB, और बाहर जाता है Q2B. सो Q2B इज इक्वल टू WB प्लस Q1B. फ्रॉम दैट Q2B माइनस WB is Q1B minus this is Q1A, and since we have assumed that Q1A equal to Q1B, so this term becomes 0. So that means this is equal to this. So there is no question of any heat being rejected. That means this is a PMM2 and its efficiency of this heat engine will be 100%. Total heat supplied jitna ho raha hai, that is completely converted into net work output, which is not possible, which is violative of Kelvin-Planck statement of second law of thermodynamics. So that means whatever assumptions we have made, that COP of A is greater than COP of B, which is wrong. This assumption is wrong. So this assumption is assumption COP of A is greater than COP of B, where A is any refrigerator and B is a reversible refrigerator, is wrong. So that means this is true. COP of B is always greater than or equal to COP of A. In fact, greater than. So any B is a reversible refrigerator. So COP of a reversible refrigerator is always greater than COP of any other refrigerator. That means irreversible refrigerator. So COP of a reversible refrigerator is the maximum between two given temperatures. So that's all. Thanks for watching.